Hello?
Yo, what's up?
What is up? Sorry for being slightly late.
No, no.
Technically.
Sure.
Um, I was just transferring all the problems to my iPad that I wanted to go over.
Got it.
Okay. Um, Alrighty. Well, I sent you a lot of different things. Um,
Hmm.
there's a decent obviously a decent amount of stuff I wanted to go over. Right before we started though,
Yep.
I wanted to discuss just like the next like my plan, I guess.
Yep.
So, okay, I took the fourth blueprint exam and I got a 506, which like I was pleasantly surprised by, so it was a 3 point increase.
Yep.
Um, Now the splits are 127 for Chem Phys, 124 cars, 128 bio, and 127 psychology, sociology.
Yep.
So like finally I got out of like the biochem like rut. I scored 126 3 exams in a row.
Yeah.
So here's the thing, like I was excited the whole day just because like it's so like satisfying to finally see some sort of like legitimate improvement.
Yeah.
But also like I was going through the exam and biochem had like two or three like metabolic passages, and then like I'm really good at like I consider it to be better at that stuff than like
Yeah.
other topics, but
Uh-huh.
I
Yeah.
don't know. I hope it wasn't a fluke. That's what I'm saying.
Oh yeah, no. No.
But
Yeah, I think the last one's like a 503, right?
yes, that is correct.
So, yeah, that's awesome. That's a great job. Yeah.
And so the next question I guess I have now, um, originally I was going to do I had 6 blueprints. I purchased the exams, but it's like right now I'm registered for September, and I know I've been bringing it up like every meeting. Like, do I want to move it? Do I not want to move it? Um, because there are like 6 AAMC exams, I was thinking, should I maybe take AAMC 1 this upcoming Monday, um, to gauge where I'm at, or do I take Blueprint 5, take one more Blueprint, and then take AAMC 1 the following week? I just want to see you've worked with so many people, you know.
Yeah, I think on your schedule we have like um I guess yeah. So yeah, exactly where I was looking. So yeah, so it seems like we start well, let
Oh
me
wait, yeah. Okay. Yeah, you had me taking, sorry, yeah, because I just basically like my thing got a little delayed because of the surgery or whatever. So like I had to skip one of the blueprints.
yeah, that's
Or like that we had in the schedule, right? So you had me taking 5.
yeah, that's fine. That's fine.
Um, then yeah, okay, so we're on the same page, I guess. I should take it this upcoming weekend then. Okay.
Yeah.
Um, you do you recommend the sample one first? Because I heard it's a little easier. I was thinking AMC 1 and then the sample. If like AMC 1 turns out well.
Yeah, I mean, I never really noticed much of a difference between the tests. I kind of treat them the same.
Okay.
So, yeah,
Doesn't really matter. Okay. Got it. All right. Understood.
but yeah, that's an awesome job with that 506 uh
Yeah.
on the blueprint.
Yeah. Okay.
Hmm.
So I guess the first one I wanted to go over. I mean, yeah, we could do this DNA question.
Oh, yeah, yeah, yeah.
Um, yeah, okay. Let's do it.
Okay, so why don't we, yeah, like tell me about how. I guess I'll read it. So a student begins with a sequence of dsDNA. What does that mean?
Double-stranded.
He adds the enzymes necessary for DNA replication, but substitutes artificial bases. So these are just artificial bases with like that prime, like apostrophe kind of added to it for the normal bases. And he allows the DNA to replicate once. So you will see, like, in order for replication to happen, you'll see like the two strands separate, and the separated strands will get filled in by whatever available nucleotides there are in the environment. So some of that will have like the primes. Um, is that like, do you know what I'm talking about?
I think so.
Yeah.
I also didn't really fully understand what they meant by like substituting them.
Mm-hmm. Yeah. So it's essentially just think of it as, I mean, they're saying it's a synthetic, but I think of it as like if it was a late radio labeled, um, nucleotides that just are different from the regular ones.
Okay.
So, um, so yeah, so okay, let's see if I can do. Okay, so let's start off with the regular DNA. Um, 3' end here, 5' end here, 5' end here, 3' end here. So that's the regular DNA. And we then place it in some environment where we have the artificial bases with the single apostrophe, which I'm just going to call prime from now on.
Okay.
So for the first replication, I mean, what happens in replication is the two strands separate, right?
What do you mean?
So like,
Oh yeah. Okay. They come apart, yes, and they're gonna both get replicated.
yeah. So first replication, these will separate. So I'm just going to do like the 3', 5'1" here, and then the 5'1", 3'1" here.
Hmm.
Okay. Now it's going to use the synthetic or whatever artificial versions of the nucleotides now to fill in the other strand for each of these. I'm going to use blue for the primes. So you're going to have this filled in, 5, 3, and this filled in 3, 5 with the G prime, C prime, A prime, T prime, right? Because that's all you have in the environment.
My question is,
Yeah.
like, what does that exactly mean to substitute artificial bases? Like,
Uh-huh. So,
I feel like I'm definitely overthinking like this sort of problem.
so like, let's say that we did not have any bases and we just did this first step where we unraveled the double strand, then nothing can go further, right? We need to fill in to make that new strand in order for it to be a double-stranded DNA. So we're going
Hmm.
to use what's in the environment. So if it's in the environment, like the prime ones, that's what is going to fill in after that first replication. Because the thing is, DNA replicates semi-conservatively, which means that half of it is conserved. In this case, it's the black strands,
Hmm.
and then the blue strands are the new ones.
Yeah.
Yeah. So, so that does that kind of make sense about like the artificial bases that you fill it in? Like if I go like more if I like kind of zoom in, let's say that, the real strand is something like ATGC. The new strand would have to be like T prime, A prime, C prime, G prime, because that's all we have in the environment to use.
Okay. Makes a little more sense, I would say.
Yep, yep. Yeah, I think the artificial bases could be a little tricky. I really just think of them as radio labeled bases,
Hmm.
so we can tell them apart. So, okay, so he allows the DNA to replicate once. Then he removes the excess artificial bases from the reaction environment. So all of the blue prime bases are gone. But what we have now is double prime or double quotes, right? That's another set of artificial bases. So I'm going to use green for that. Or rather, before I do that, I'm going to do this. Because every time you replicate, since you have the two strands, you're going to produce two different things. And so we can go through like just how we did like the first replication where we open up the double helix and we fill it in. We're going to do that for this as well. So first, I'm going to keep the black. I realized the 3' and 5' could be a little confusing because of the primes in the artificial bases, but you can kind of like tell, like, right, that I just mean the ends. But so yeah, so this is gonna unravel, and the black one would be, whoops. So we would get here a black one that's 3 to 5. Here we can get a black one that's 5 to 3. We can also get this blue one, which is 5 to 3, and this blue one, which is 3 to 5, right? Because we're just opening up that double helix to get that single strand, which we will then add the new artificial bases to.
Yeah, but how about the double prime?
Yeah, so now we're going to do that. So I'm going to use
Oh.
green for that. And so now this would just be, oops. So now this would just be whatever, 5 to 3. This would be 3 to 5. This would be 3 to 5. This would be 5 to 3. So that's after the second replication with the double prime artificial bases.
Hmm.
And I'll say like first replication, second replication. Now, they say that after this, they let the DNA replicate 2 more times. So we're going to do that again. So we can have this. And I'm gonna just, yeah, start with the black. Oops. Black one here, the black one here, the green one here, a green one here, a green one here, a green one here. Then a blue one here and a blue one here.
Tell me on the exam I'm gonna be doing this.
Yeah, I mean, it'd probably be a good one to make a guess on flag and move on.
Okay.
I haven't looked at the choices yet, so maybe once I finish this, I can
Yeah.
figure it out that way. But yeah, so now this one should now have the replicate 2 more times with just the green, because we're still in the double prime environment. So green, 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 green. So okay, and then they said the end, how many how can the DNA molecules be molecules present be described with regard to their composition? So let's see, 2 GCTA slash GTCA. Wait, the symbol slash separates the 2 strands. Okay, so these are just the black ones. These are the, so they're saying 2. Okay, so let's see. I think we should have, so like, okay, if the blue, so like, let's do this. So black would just be this. Blue would be whatever, like this. Then green, like this. So we see that ultimately we should have a lot more of the green type. Right?
Mhm.
So if we look at, okay, so I guess if we look at this, we see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's see. Okay, so we got, so, okay, maybe I can do it like this. So we have in our final replication, we have 2 of the black ones. So I'll just say 2 of these. We have 2 of the blue ones, and the rest are the green ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now if we look at the choices, A says 2 of the black ones, 2 of the blue ones, 4 of, oh, sorry, that means that they're bound to each other. Like, sorry, like the slashes mean that they're bound.
Yeah.
So I'm going to adjust this. Oops. So at the end, we don't have, well, we have 1, 2, 3, 4. We have 4 of these guys, right? Um, okay, so yeah, we have 4 of those. We don't have any. So what I mean is we have 4 of because the slashes mean that it's for each strand. And we don't have any other, like we have green binding with green, but we don't have blue binding with blue. We don't have black binding with black. So that means that we can eliminate A, because A says that and that. What I underlined. So two of like the regular unprimed. What this looks like is the two black ones.
Okay.
And then the two single prime ones is just looks like just two blue ones. All right.
Yeah.
And
I got you.
yeah, so at the end, we don't see that. We do see the four green ones. At least that part's right, but the first two parts aren't. So A is out. B says two black bound to blue. So like blue, black, and like two of these. So let's see. Doesn't seem like we have any blue binding to black here in the last
Yeah,
replication.
so it'll be C, right?
Two black greens here, here, and here. Two blue greens, which we also see. And then four green greens. Yep. And then D would be wrong because that would be like the random, because there's like, like the three models, it's like dispersive, conservative, semi-conservative.
I don't know what dispersive is, actually.
Yeah, I think dispersive is essentially the same thing as a random.
Okay.
So yeah, so D would be out. So yeah, it would be C. Now, in terms of answering this more quickly, let's see. I guess you would want, because we know that we're going to have more of the double primes, but A, B, and C all say that there's more of the double primes. Yeah. Okay, so maybe you can see from like this type of replication here that since it's semi-conservative, you're going to have in each replication half of one type and half of the other type. Like let's say half black, half blue, something like that. And as you keep going, and we don't have any more of the like original type of artificial bases, we should stop having them bound to one another. So we should no longer have two blacks bound. We should no longer have two blues bound. So that could be a way to do it faster, but yeah, I can't think of a way other than
Okay.
yeah.
Let's move on to the next one.
Okay.
Uh, the it was the oscillator antinodes
Yep.
discrete thing, yeah.
Oops. All right. This one, right?
Yep.
Okay. So yeah, how would you do this? What's your approach here?
Um,
Or maybe we haven't talked about this yet.
we haven't really. Um, yeah, I don't really know. I mean, at first I like tried taking the slope. I mean, it ends up being 50 Hz, but
Yeah, so in harmonic resonance, there's ultimately two types. There's even, which could be like open, open, close, closed.
hmm
There's odd, which would mean like open, closed, closed, open.
yeah.
And like I don't know, a mnemonic I use is like when I see someone with a guitar, I envy their tool.
It's a nice one.
Yeah, because a guitar is an example of scale.
Yeah.
Exactly. So, okay. So what does that mean? That means frequency. I put a subscript n here is equal to nv over 2l,
Mhm.
and the 2l just comes from the fact that if you had something like, let's say, like this, it would be like, let's say, something like that. And if you had another one, it can be something like this, showing you that, and if this is L, 2L is one wavelength.
Yep.
And we also have now, we could also have open on both sides. And that would look a little different. It would look more like this. And what's the significance? So if it's here or here, it's considered an antinode.
Yep.
Yeah. And then for this and this, they're considered nodes.
hmm
And as you go, oh, and then when I wrote this formula for the F, this N value is, well, it starts with 1, meaning it's the fundamental frequency.
Yeah, yeah, yeah.
Yeah, and it can go up to like 2, 3, 4, 5, etc.
The other one is 135.
But yeah, for the odd ones, it's gonna be, yeah, 135. And so they're telling us that one end is attached to a wall and the other connected to an oscillator. So that's kind of like, you know, closed on both sides, right? Both ends.
Yeah. I mean, it was hard for me to picture personally. I
Okay.
thought it was like I wish they gave a picture, but um, 'cause what exactly is an oscillator? It just makes it move.
Yeah, yeah, yeah. Like back and forth. So like simple harmonic motion involves oscillation back and forth, back and forth. I remember I first learned the word when I was a kid, and a fan has like, I don't know if they even make fans like this anymore, but like if you pull something on it and it says oscillate, it will, like, the fan will,
Yeah, yeah.
you know what I mean?
Mm-hmm.
Oh, yeah. So oscillate means to go back and forth.
Okay.
So, and yeah, what I'm picturing here is just like, let's say I'm holding a rope and at the end, it's being held by some other person at the end of like whatever, and that person is moving the rope up and down,
Yeah.
causing it to oscillate. So yeah. So okay. So oh, and then as you go up from like fundamental to like, that second harmonic, and forward like that, what you'll see is that you're adding a node and you're adding an antinode.
All right.
Yes. So what they're saying, so like, okay, so that means so they're asking about, okay, so they're giving us number of antinodes. And since they tell us that it's closed on both ends, it's this example here where there's one antinode, right? Over here.
Mhm.
So if they say that there are two antinodes, that would be, I'll use blue. So like one antinode's here, one is here. So two antinodes means 2L, right?
But why couldn't we just figure it out that it's going to be 2L because of the fact that it's closed on both ends?
Yeah.
I
So
mean, you just did, but just like I guess a different way. I'm just saying, like, if we already see that they literally tell us that it's closed, right? Because it's connected on both sides. Right away, we know we can use the formula like 2L over N or NV over 2L.
yeah, so we are going to use this formula. It's just a matter of what do we put for n,
Ah, okay.
right? Because they don't,
Yeah,
tell us
yeah.
by telling us that, what free, like if this is like this first harmonic or whatever. They're just telling us the number of antinodes, and so we have to, figure out in which case you'll have two antinodes. And the basic idea of adding an antinode and a node for each. There's a good uh drawing here. Something like okay, whatever, I'll just find it later. But
Mm-hmm.
but yeah, as you go up in n, you add found it. Okay. So this includes both uh odd on the left where it's open closed, and even on the right where it's, in this case at least open open, but it would be the same or similar if it was closed closed. But we could see that if we focus on the the ones on the right, for this we can see that there's two antinodes. So two antinodes, I'll just write an, one node. And then when we move to the second harmonic, we gain an antinode. So we have now three antinodes. And we also gain another node. So now we have two nodes, right?
Mm-hmm.
So like this third harmonic should be four antinodes and two nodes. So let's make sure. One antinode, two antinodes, three antinodes, four antinodes, right? Four antinodes. And we should have how many nodes?
You're saying where?
For this third harmonic. Because you could see as we go up, as n goes up, we are simply adding one antinode and one node.
Three.
Yep. And let's see, right? One, two, three.
So for an even one at the second frequency, there's three nodes. What's the fundamental frequency? Wait, I'm talking about,
Yeah, so
this is an open one.
yeah. Um yeah, if it's closed, it would just be, so maybe I'll write in purple for like closed, it would just be the reverse. Like instead of having two antinodes in one node, you will have for this first harmonic, two nodes and one antinode. And then each time you'll increase it by one for each. So this will be three nodes, two antinodes, and then this one over here would be four nodes and three antinodes.
How would you draw that though? So it's
Yeah.
um okay. I think I
Uh-huh.
is it just like two nodes? That means on both sides it's in the like middle. It's
Yeah.
like half of that thing. Yeah.
Yeah. Mm-hmm.
Okay.
Yeah. Yeah.
Okay.
So that's the clue that we use here to be able to answer this question. So the questions, so they tell us that it's closed on both sides, and they give us the number of antinodes, and the two antinodes, like if you remember that for closed, you're gonna have more antinodes. I'm sorry, more nodes than antinodes. Like if this was, open or whatever, this two antinodes would be the fundamental frequency, right? Because of this. But since it's closed, it's going to follow these rules where the fundamental means one antinode. So the second harmonic is where you have two antinodes. So when they say here number of antinodes, two, that's what they mean. They mean that second harmonic, aka n is equal to 2 for this. But you can use any of the values.
Okay.
Is that kind of
I mean, how do we so we just gotta know? We gotta know this stuff. We gotta remember, right? Like
yeah.
so before I only thought there was two types. I thought there was just closed and open. I mean, I guess there technically is still, but like
Mhm.
so let's say you have it open on one side
Yeah.
and closed on the other. Do you still use NV over 2L?
That's when you would change the 2L to be 4L. And the reason for that is because this thing that I drew here, like, or I'll just use this picture. So you could see so this is like the odd stuff. You could see that we just have one node and one antinode. Okay. Now, if I drew that like this, kind of a bad drawing, but if I add another one, it would just be like going back down like this. Let's say like, yeah, that's not.
No, don't worry. It's a beautiful drawing.
But the idea is that if this is a node and an antinode, it's the same thing as something going up like this. So then the next one will go back like this. The one after that will go down like that. And then the fourth one will go back up like this. So that means, let's say this is something like that, and then whatever. It essentially just proves that one wavelength is 4L. Because for the closed, we could see that each, like the length is half of the wavelength. So to go from this, so it's like this full sine curve here, right? If I was to put like horizontal values here, this would be like 0, this would be like 1, this would be -1. So you see here, it starts at 0, it goes up to +1, goes back down to 0, goes down to -1, goes back to 0 to fulfill that entire sine curve. So that's why the wavelength is 2L for even, but it's 4L for odd.
Okay, and now how about open open? That's
So
is that the blue? Yeah, what is open open then?
so that would be like something like this, except instead of having like this part, like the crest, it's going to be in between the two.
Oh, okay.
Yeah. So like
Okay.
that.
Okay.
Yep. So good. So, okay. So they're telling us, yeah. So we can use like one of these values, as long as we put in the right value for n. So let's see if I use n as 2 as the number of antinodes. Well, I shouldn't say that. I should say if the number of antinodes is 2 for a closed, which is what this is, that means that it's the second, it's the, oops, it's an n is equal to 2, the second harmonic. So here I'll write like if 2 antinodes for closed, what that means is n is equal to 2.
Yes.
Okay. And so we can plug that in for n, and then using the table, we can plug in the frequency, and then they give us the value for L, which is half a meter, and then we can solve for velocity. So I would first rearrange. So V is equal to F times 2L over N. So that will be 100, I'm just going to write 100 hertz. Times 2 times 0.5 is just 1. Divided by 2, which would give us the 50. Like meters per second.
Wait, so N means antinodes for like all the time when we do these problems or no?
No, so n just means,
Okay.
yeah, like fundamental frequency, n is 1. The second harmonic for the even will be n is equal to 2. There is no second harmonic for odd, so it goes right to 3. So that's when n is equal to 3. But yeah, it can, the number of antinodes could give you, is going to give you the clue about what n could be, but it's not necessarily the same.
Okay. Can you check your email? I just want to make sure that I drew it right.
Yep. Let's see. Closed. So, okay. Open, closed. Yep. Open. Yep. That's right.
Okay. Hearing that yep is so satisfying. All right.
Yeah.
Thank you, thank you.
Yep.
All right. Okay, so um just to make sure, right? So they gave us the frequency and you just plug it in, right? Wait,
Mhm.
wait, can you go down? I just wanna Oh, right, they gave us length too. Okay, yeah.
Yep.
I got it.
Mhm.
Okay. Makes sense.
Yep. So, okay, let's see. I think this was
Yeah.
all right. So let's see. Patients who have undergone kidney transplant surgery often display reduced osmoregulatory capacities compared to healthy controls. Which of the following graphs shows how kidney transplant likely influences the response of plasma sodium concentration to water intake in kidney transplant patients versus healthy controls? All right. Okay. What are your thoughts?
So, I mean, um, if you have reduced osmolarity, osmoregulatory capacity, like if something has more salt, it's the water's not just gonna follow it. My understanding.
So, um, so tell me what would happen in like a healthy control. I guess yeah, tell me more about what you're saying.
Like if you have a cell, right, you have the hypotonic, hypertonic, um hypertonic is when there's more salt
Okay.
outside, water's gonna follow.
Yeah. So so okay, since the x-axis is water intake and the y-axis is plasma sodium concentration, we can we want to see what type of relationship could exist between the two.
Right. Okay, so um I guess if you take in more water, uh your sodium wouldn't really change, right? I didn't realize that when I was doing it.
Um,
Or I don't know.
yeah, so if you have a lot of sodium in your blood or your plasma, um, your body is gonna try to dilute that, right? Um, so for instance, if you drink a lot of water, you're going to dilute the sodium concentration in your plasma. Um, so what type of, you know, things should we see on a graph relative to that shows the relationship between water intake and
See.
plasma?
Well, for health controls,
Yep,
being C.
good.
So that doesn't really have to do with like hypotonic, hypertonic. It's not really that.
Uh, so kind of, I mean, because I'm thinking also about like what happens in the nephron, and And we know, like, as the descending loop of Henle, like, well, in the nephron, like the cortex, the outer portion has like a relatively low osmolarity or a low sodium concentration. And as you go deeper into the medulla, the osmolarity increases, which means that water gets reabsorbed. And if that happens, that means that the plasma sodium concentration should get more diluted, therefore smaller. So we should see that for a healthy control. And now for the kidney transplant, I see various answers that talk about it going like up as or down as the water intake increases. Kidney transplant, healthy control. Oh, you said that this question's answer was D.
Yeah.
Okay. So, all right. So I eliminated A and B just because I know that they shouldn't be working in opposite directions, because if they say that it's a reduced osmoregulatory capacity, it would just mean that it isn't going to be functioning well. So it shouldn't go in the opposite direction. So between C and D, let's see. Okay, you know what? I guess it makes sense because the healthy control should, like, exactly what I was saying about, like, if you drink a lot of water, your body will react, or your kidneys will do what they need to do to keep that plasma concentration constant compared to the person with a kidney transplant. Like, let's see. Okay, so we should know that increased water intake, dilution of salts, so inverse proportion between plasma sodium concentration and water intake. Now, between C and D, I guess D would make sense because you have less of that ability to keep the levels constant to maintain osmolarity. So in the kidney transplant patients that have reduced osmoregulation, they're not going to be able to maintain a stable amount. And you should also just think that, if we're increasing water intake, what we're essentially doing is we're diluting it. So healthy control should be able to maintain a stable plasma concentration of sodium with changes in water intake. But the ones with the kidney transplant would be struggling to maintain that consistent concentration. So what that means is as you increase your water intake, your plasma sodium concentration goes down, and osmoregulation would want it to stay constant. I think that would be how we could answer this.
I mean, it's still kind of confusing, but I guess, yeah, I mean, I just don't understand why if water's going up, how's concentration staying the same? Like,
So it's like when, in the um, in the nephron, when you go when it goes to a region of higher um concentration of solutes, aka osmolarity, it will pull water out, um, causing it to be reabsorbed. And reabsorption just means that it gets reabsorbed into the blood, aka plasma. And so it does this to maintain that same osmolarity. So in this, here's like a figure here. Or this one. So we could see that the cortex, well, I guess it doesn't even really tell you, but basically the cortex has a really low osmolar concentration of solutes. So if I go down like this, I am increasing solute concentration. And if you're increasing, oh, and it's kind of like what you said about hypertonic, hypotonic, like as we go down from the cortex into the medulla, since the concentration of solutes are increasing, it means that we're going to have a hypertonic environment. And if it's a hypertonic environment, it means that water is going to want to leave that environment, which is why you have water reabsorption here. But what you also have in the ascending limb or limbs is reabsorption of sodium, which, by the way, is done through active transport, because the region is high in sodium anyway, so it's going against its gradient. But this is a functioning kidney. So if you could imagine, the greater amount of water that you take in means that you will have a smaller amount that gets reabsorbed, right? Which means that you should have a smaller amount of sodium chloride reabsorbed as well in a functioning kidney. But if a kidney does not function in this osmoregulatory way, then it's going to have an imbalance of water to sodium. And all you need is an imbalance of one of those things. Like if you have less water, your sodium concentration goes up. If you have more water, sodium concentration goes down. So for this question, where we see the different plasma sodium concentration and the water intake, we see that it's constant for the healthy control because its osmoregulation is working properly. And osmoregulation, again, is just keeping the water in your body kind of consistent with the sodium so that you have that you can maintain a consistent amount. But if you have the kidney transplant, you're going to get this downward dotted line, which essentially shows that as you increase water intake, the concentration of sodium goes down because if we go back here, we have enough of this water. So we don't need to draw it out. When I say draw it out, I mean pull it out. And if we don't need to pull it out, we don't need to pull out the sodium either. So generally, I would say to see it like this. Healthy things, generally speaking, especially if they're saying it's healthy because it's good at osmoregulation. Regulation, right? It's not one or the other, right? I mean, when I say one or the other, it's not like we're increasing osmolarity or decreasing osmolarity. Osmoregulation means that we have in our bodies a way to maintain that homeostasis so that if we have too much salt, we make up for it with water and vice versa. So osmoregulation is the keyword here. And when you see things that are like regulation or modulation or something, think of things that would make it so that certain things will be consistent or constant. And if something gets messed up, like if osmoregulation gets messed up, then you're not going to have that constant amount of water intake to plasma concentration.
Mm-hmm.
So, so basically, if you drink a lot of something, or if you have something with a lot of sodium, your body is going to react in such a way to reabsorb water to dilute that. But if your kidney isn't working, drinking more water is not going to fix that osmolarity. It's not going to be able to keep up with the ability to maintain that osmolarity.
Huh.
So, so in the healthy person, we want it to be a constant amount. And that's generally going to be the case for whenever they ask you about something that's involved in regulation.
Mm-hmm.
Mm-hmm.
Okay. All right.
Yeah, so I'm going to write. So healthy osmoregulation means constant values for for sodium, so for plasma concentration of sodium and water intake.
Okay. All right.
Okay. Let's see their next one. Is okay. All right, so for this, why don't you tell me what you're thinking here?
Says fail to load, like on the screen.
Okay. All right. What about now?
Yeah, I mean, in this problem, I was just not sure whether or not it'd be a linear exponential curve. I wasn't sure how to, pick the correct answer.
Mhm.
So like between A and C. Um,
I see. Got it.
yeah.
Yeah. So resistance is resistivity, which is this rho
Yep.
L length over A. Now,
Mm-hmm.
resistance versus temperature would be a linear relationship. But since you're asking for the um resistivity, or let me just take a closer look. So resistivity increases with temperature. As the current passing through the wire increases, the temperature of the wire increases. Values of voltage across and the current through the wire are measured. Which graph shows how voltage varies as the current I is increased. Okay. So voltage versus current. And okay, so let's see. So they're saying that resistivity proportional to temperature, current proportional to temperature as well. And we know from Ohm's law that voltage is proportional to current, right?
Yeah.
So if current is proportional to temperature and voltage is proportional to current, that must mean that voltage is proportional to temperature. Now, that actually would lead me to the linear choice. So I'm going to see what else I can do here because there should wait, okay. Okay. There's going to be a nonlinear relationship between let's see. Voltage and current. Oh crap, I see. I see. So the resistance is the resistivity times length times area. So I plug that back into Ohm's law to see that voltage is proportional to both like the I times the, I'm going to kind of forget about the length and the area here, multiplied by the resistivity here. And if it varies with both of these, that would mean, and we multiply the two, that would give us an exponential. But what we can also do is we can think about power, because a lot, so like these types of questions, you'll see them ask about power, because power would be kind of like the rate at which energy increases or is dissipated and released to the environment. So yeah, so if we think about it that way, let's see. Yeah, I guess the best way would be like just seeing that voltage is proportional to current, and it's also proportional to resistance through resistivity. So since it's based on both of those things, it would be like as if you multiplied the two, giving you like an exponent, since it depends on two things.
It says only as current increases.
Yeah.
Is it because resistivity also increases?
Yep. Because they said current increases, as temperature. So basically this and this both increase with temperature, the rho and the current.
Makes sense.
And voltage is proportional to current. It's also proportional to resistance, which means resistivity, which is, oops.
I get it. I get it.
Yeah.
Yeah, but
Mm-hmm.
so freaking tricky.
Yeah.
Like like you could say what is volts? I mean, they said at the beginning, I guess. It's just like
Yeah.
okay, it makes sense. It makes sense.
Yeah. I mean, as long as you're able to, like, I'm guessing you were able to eliminate B and D.
Yeah.
Yeah. So, yeah, this is a super tricky one.
Okay. Next, I just sent you a problem. I know there's like one with an actual passage. Let's do that like right after this one I sent you.
Okay.
Just because I think this get it out of the way, this one. Wait, let me know if it went through.
Okay, yeah. Oh, it's another one of these. Okay.
Yeah.
So here we go. Okay. So an elastic cord vibrates in the fundamental resonance. So we know n is equal to 1 between two fixed posts. Oh, and we also see two nodes and one antinode. Um, okay. And we also know that it's closed, because say if two fixed posts. And then this is L, this is that, half wavelength thing. How will the fundamental frequency change if the cord is stretched and then attached to the same post again at a distance L apart? Stretching it. Stretching it. Okay. My thoughts are, I mean, I'm imagining like a rubber band, and if you like pull down on it and let go, it like does,
Yeah.
right? So my guess is that it's gonna increase perhaps the frequency.
Hmm. Yeah. It's just like in the answer choice, they give like the
Mhm.
surprisingly only 27% got this right. They give like
What was like the most common answer?
the most common answer was B, but it
Yeah,
was decently like evenly
yeah,
distributed.
got it.
Um, they give the relationship of how velocity increases as core tension increases. Um, yeah, apparently the square of the speed of a wave on a chord is proportional to the tension.
Yeah. Oh, yeah. Okay. Okay. All right. Um. Okay. That makes sense.
Wait, but like if there's okay, never mind. Okay. Yeah, I mean the way you thought about it, I guess made it super easy. Um I was trying to think of how tension was connected to frequency.
Yeah. Let's see if we can do this like, well, whatever, algebraically then. So,
Yeah.
but yeah, I actually forgot about like that tension part. Okay. Let's see. Well, I mean, okay, tension should be proportional to velocity and also, well, force. Okay, so if we're trying to do relationship between velocity and velocity and tension, tension is a type of force, and let's see, tension is a type of force, newtons over. Okay, I think there could be a we can see. Okay, So I think,
It's
yeah,
like, I mean, like I just don't want to like we don't have to spend too much time on it. It's also discrete, so it's like, but
I think
yeah,
there's a formula for this that I haven't seen in a long time. So I was surprised
okay.
here. But it was something like yeah, something like this and like inversely proportional to like mass. It was something like that. But but yeah, hopefully uh yeah, hopefully I guess it made sense like conceptually and hopefully they won't ask this. I mean, if you see them ask this type of thing again with some type of formula, I can yeah, I can send that. I could send that along.
Yeah, they said
Yeah.
first a standing wave of a fixed wavelength, frequency, fundamental, resonance, standing wave increases. Also, what is exactly a standing wave?
So it's a wave that stays in one place. So like rather than, a sound wave or a light wave that travels. So like, you know, um like this thing or like, on a guitar string or on a swing set, you're going back and forth, but you're not the wave entire the entire wave isn't the thing that's moving. You're it's essentially staying in the same place essentially. So yeah, so just think, oh crap, okay, I see it.
Yeah.
My notes, okay. Velocity of the wave on a string, square root of tension divided by mu, which is mass per liter. Sorry, mass per length.
No,
That's
no, I've seen that before.
yes, that's the yeah, that's
V equals square root of tension over linear density.
yep. Mm-hmm. Yeah,
Okay, that would help us, right? Here. Okay,
yeah.
so I should probably memorize that. It's like such a rare formula.
Yeah, no, I haven't seen it in a very long time.
Okay, I understand.
Okay, yeah. All right, and then what was the other one?
Other one as in
I think
what?
you mentioned another question with like a passage attached or something.
Oh yeah. I should have sent that to you. It might be like in the other email chain.
Oh yeah, let me see.
Oh no, it's in the same email chain as this problem.
Okay.
So yeah, side chain of histidine. That's what it starts with.
Oh yeah, I remember seeing that one. Okay.
Yep.
Yeah, by the way, if you see more questions like that involve like that formula here, to make that, let me know. And
Okay.
yeah. So
Let you know, just
yeah, like
like send it to you.
you could send it to me, but let me know like, if you see that, if they ask something like that again.
No, because I have a problem saved. Like I understood it, but if you need me to send it to you, like I can. You know what I mean? Like
Oh, I just mean for this. Like,
yeah.
okay, all right, okay. Yeah,
Okay.
got it. Okay, let me see. Oh, okay, I see it now. All right, so yeah, the histidine. This is good to go over because that's like the weird one, it's a basic one, but it has a pKa less than 7. Took me a very long time to kind of understand how, like, yeah, why. Um, so okay, let's see. Allowing it to readily exchange protons with an environment at pH levels near pH physiological pH. For this reason, it's found in active sites. Some theories think that dipeptides containing two histidine residues, provided the catalytic activity required to generate more complex peptides. Indeed, when glycine is incubated with his, the rate of polyglycine formation is increased significantly relative to glycine under identical conditions, except with his absent. Okay, it's hypothesized that his formation was a critical step in the eventual formation of proteins. To test whether his could spontaneously form in prebiotic conditions, 4 milligrams of free histidine was dissolved in 1 ml of aqueous solution and mixed with condensing agent believed to have been present on prebiotic earth. This was repeated with solutions at different pH levels. The solutions were then heated. Water was allowed to evaporate, blah, blah, blah. Okay. Phosphate buffer amount of his recovered after evaporation of solutions at various pH levels. So 5 pH, amount is 0.16. Seems like its pH goes up at least still within physiological pH. The amount of his recovered goes up. Okay. Now, based on the pKa of the histidine side chain, given the passage, which best describes the charges of the his dipeptide chains at pH of 7? Yeah. So yeah, so histidine is always a confusing one because we are typically thinking of basic amino acids as having a positive charge, right? But in actuality, it's just a small amount of the histidine with the positive charge, but most of it is a negative charge. No, what I'm talking about, most of it is a neutral charge.
Yeah, I was confused just like about why it's smaller percentage. That was my thing.
Yeah, so you said smaller percentage for like tell me what you said again.
Okay.
All right.
Uh,
I'm looking through like the Anki deck that I made about histidine, but tell me what you're saying.
I was just saying it was between A and C, and I chose A because I was not sure why it was small percentage. The explanation had something about like uh Hasselbalch, Henderson-Hasselbalch equation, and like the ratio, and it's like they just made it super complicated. I was like, okay, I have to ask you.
Yeah. So yeah, okay. Got it. Here we go. So yeah, I titled this "What the F is up with histidine?" Does it show up, or is it giving it like an?
No, I see it. I see it.
Yeah. So okay. So side chain has a pKa of 6, so its isoelectric point is you know how to calculate that, right? Like um right? Do you,
Yeah.
yeah. Basically like well, for a regular one, pKa of the C terminal, pKa of the N terminal, average of the two. for acidic ones, you take the two smaller ones and you take the average. For basic ones, you take the two larger ones. So here I took the two larger ones, 6, the side chain, and 9.2, which is whatever the N terminal. Average is 7.59. So that means, so isoelectric point is the pH at which something exists as a Zwitter ion without a net charge. So that's 7.59. Physiological pH is lower than that. So I wrote, why don't we use Henderson-Hasselbalch to figure out how much of it is protonated and how much is deprotonated at physiological pH 7.4, followed by pH of 7. So I wrote out Henderson-Hasselbalch, and I plugged in for pH 7.4. I plugged in for pKa, the pi, 7.59, and then the log stuff, I subtract the whatever, 7.59 on both sides, and then I do the log to figure out that the ratio of the conjugate base form is the or the ratio between the two is 0.65, so only 0.65 or 65% of it is deprotonated, and at a pH of 7, if you do the same math, you get only 25% is deprotonated. So that would mean that, like, essentially what this tells you is just that it's not all going to be one or the other. It's going to be a mixture of some being protonated, some being deprotonated. So for the question 7, first of all, always be careful with the words all, and be careful with those. And then C and D says most but small percentage. Now we know that the type of ion or the type of charge that histidine can have is positive. So that's another reason to eliminate A, but it can also be a reason to eliminate, well, actually D. Okay, so between C and D, it's just that C is saying that a small amount are positive, and D is saying a large amount is positive. And I mean, when you said the math involved or the explanation about Henderson-Hasselbalch, was it kind of like what I did here?
Yeah, I
So
think so. Let me double check. But
sure.
yeah, yeah, like I'm pretty sure it was that. Um, Wait, okay, actually, no, there wasn't even Henderson-Hasselbalch. I'm confusing it with a different problem.
Okay.
Um, oh wait, I, yeah, they still mention Henderson-Hasselbalch. Uh, Never mind. Take back what I said. They did use it. Sorry.
Okay. Okay.
I'm trying to. Okay, there we go. I found it. Like it wasn't directly in the UWorld explanation. You had to like click on a hyperlink.
Hmm.
But yeah, hold on. I sent it in the Zoom chat, but it was just pretty overwhelming. I don't know.
Okay. So, okay. So, Okay, so they said 7. Okay. Let's see. Okay, okay. I see. So I think what I did in this green thing is I just used the isoelectric point, but maybe I should have just oh okay, okay, I see. Okay, okay. So based on the pKa of the histidine side chain given in the passage, so I should have used pKa of 6. So that's the clue here. So what that means is, pH equals pKa plus log A minus over HA would be 7 is equal to 6 plus the log again, A minus over HA. Subtract 6 on both sides. 1 is equal to the log of A minus over HA. Get rid of the log by taking it to the power of 10. So 10 to the power of 1 is equal to the concentration of A minus over HA. And this is essentially then telling you that that the if I solve for the concentration of A minus, which is the amount that is deprotonated. Let me see over here. Is protonated percent. His H. Oh, his H is okay. The protonated form. Did I even talk about that? His pH 7 charges of the his dipeptide chains pH of 7. So this trying to see the protonated forms. But I guess that's what we're asking. So I guess we're then looking for the HA part. Okay, so I mean, I have it set up, but what they're doing here before the Henderson-Hasselbalch is they're looking at percentage I see. They're looking at percentage of the histidine that's positively charged, and that's equal to the concentration of the histidine that's positively charged over the total histidine, and then they rearranged it, or rather, then they equated the total as the regular histidine plus the protonated histidine, and then they plugged that back in to get the percent here. And then when they used Henderson-Hasselbalch, we are going to be solving for the amount of histidine in terms of protonated histidine. So that's so this is the step that I got up to over here. 10 times the protonated version, 10 times HA is equal to the A minus. But then the percentage part comes in. And so we would know that the percentage is going to be the regular histidine divided by the total. Or rather, if they're asking for the amount that's protonated, we can just have that amount up top and then the total on the bottom. And then we have this. So it's essentially like so yeah, so I mean, I essentially get like 1/10 here.
Yeah.
And, they're like 1/11. So yeah, so okay. So basically, you could use the Henderson-Hasselbalch here, and the question stem kind of helps us out by telling us to use the pKa of the histidine side chain. And we just kind of went from there. So that means that the amount that has a positive charge, which is the HA, is 1/10 of the amount that does not have the positive charge, which is A minus. So that means that we can eliminate D because most of the side chains have a charge of like the non-protonated one. So I'm going to write like a little caveat here because it seems like, HA is what you use for like the acid and A minus for the conjugate base. But I really mean HA to mean the protonated form of histidine, and A minus, I mean regular non-protonated histidine.
Yeah.
And then also for this question, for this question here, they ask about the side chain only, not the entire molecule. I mean, in my calculation here with the PI, I was doing that to calculate for the entire molecule, but they want us to just figure out, or just to use the pKa of the side chain, not the entire molecule. So that's why in the answers here, we see the His is just that, and the protonated version is just that. It's just affecting that side group. It's not affecting the entire molecule.
Okay.
Yeah. But this could also be one to I generally hate telling people to memorize stuff, but for histidine, it's gonna be worth it to memorize, or at least, remember that it's that weird one. That means that it will, like the other basic amino acids, have a positive charge, but a small percentage of it will actually have a positive charge. Because I know there's I remember seeing an AMC problem that gave you like a list of amino acids and they asked like the charges essentially. And when you do it, the H that they have, you would normally, I mean, I would normally put as like +1, but it turned out to be 0. So just remember that, I can write it. Just remember that for histidine, 10% is positively charged, 90% is neutral. And yeah, that's that.
Okay.
Mhm.
And so for the next question, it asked about like separation techniques. I put A, answer is B, or it might be the other way around. Um,
Let's see.
but yeah.
To separate his from monomeric histidine. Okay. Um, how did the his form again? It was just a regular dipeptide, I guess. So dehydration synthesis, I guess. Um, Gel electrophoresis would help if we had like a denaturing or reducing. Um, but it seems like his I mean, like, so that would work for like larger proteins. But it seems like we're just talking about a dipeptide of two histidines attached to one another. So, so yeah, we probably won't be using gel. Um, Spectrophotometry, I mean, uh, that can give us information about, I guess, what the molecule looks like. But let me see. Okay, northern blot. That's like RNA, right? Snowdrop or whatever. Like southern blot for DNA, north
Yeah.
high performance liquid chromatography. I'm kind of forgetting what that was. Is that I'm thinking maybe if that's the same thing as
So HPLC is just basically similar to TLC, but a HPLC uses pressure, from what I remember.
okay. Is it similar to well, okay, like okay, chromatography will always take advantage of differences in affinities for mobile phases and whatever phase, stationary phases. Liquid high performance liquid chromatography. I mean, I'm kind of imagining for some reason like gas chromatography, just because that also involves like, well, okay, let me see. So, um, separate it from monomeric. So spontaneously, okay. Heated, evaporate, blah blah blah. Let's see. Okay. So Okay, so it's a small molecule. And okay, if it's since okay, the gel will separate things based on size, but and sure, we could have a different size between the peptide and the monomeric uh histidine, but I think that they're still too small for gel electrophoresis to really work. And also gel electrophoresis works best for like when you have like more than a primary structure, like secondary structure, tertiary structure, because then you can denature it, you can break disulfide bonds, things like that. So not sure about, I don't think it would be a spectrophotometry. Now I was thinking about that because I know that things that you can use light for would be things like molecules that are very that are aromatic um and have a lot of conjugation. And histidine does seem to have that. However, both the dipeptide of histidine and histidine alone should have that. Should be able to
For the same amount of it, or
what's that?
like the same amount of conjugation, or what?
Yeah, they should have, I mean, I guess like, the dipeptide or the di version would have twice as much, but I
Yeah.
still think that that's a little too close. Same thing with like gel. Um, and then Northern Blot, we know that that's not going to be it. But now, okay, high performance liquid chromatography. So, good chromatography, high performance. I mean, you're going to have a. Oh, you said something about like pressure forcing something, right?
Yeah.
Okay. I want like just like a nice image of this so I can visualize it. Oh, okay. So it has like the okay, maybe. Okay, so I think what we could do for this problem is since the histidine and the his dipeptide are so similar, like theoretically, gel electrophoresis could work because it separates based on size, and the his is going to be like double the size of just one histidine. But it still seems like it's cutting it pretty close. It doesn't seem like it's the right job, like thing. It doesn't seem like it's the right uh thing for the gel to do. The gel is going to be better at distinguishing like 150 kilodalton differences and stuff like that. Um, and the spectrophotometry, I think maybe, I mean, like we should get the same absorbance at the same wavelength or whatever. maybe you'll get a little bit more intensity for like the his rather than the monomer, but it still seems like it's not it's both A and C seems like kind of like blunt instruments to kind of be able to separate something that's so similar. And so high performance liquid chromatography is what I'm imagining is first, if we don't have high performance and we just had liquid chromatography, yeah, we're going to be doing it, whatever, based on the different affinities for the different mobile phases and stationary phases. High performance, my thoughts are that that means that you would be able to have a greater resolution, meaning that you can separate things that are hard to separate through other means because it's so good at showing that type of separation. So I think that HPLC is just like the same principles as like TLC or regular liquid chromatography. The high performance part just means it's a higher resolution. So you can see the differences between, because like if I were to draw a gel and let's say whatever, like let's say his is like somewhere here, let's say like, I don't know, like 35, whatever, Daltons or kilodaltons or something, like I guess then, or rather the monomer could be this, and then like the dimer could be this, but I feel like it would still be too small of a difference. Oh yeah, because like an amino acid is like 110 Daltons. So you would really have like 100 Daltons here and then like 200 Daltons here. But we're used to seeing for gels really big differences, like 300, like 660 like kilodaltons, and then like whatever 25 kilodaltons. So I think that gel electrophoresis is not able to find and be able to have as fine of a resolution in determining the difference between the two. And spectrophotometry, I think, is the same type of thing. It's not going to have high enough resolution to distinguish between the histidine dimer from the histidine monomer because they're just so similar. Um, and liquid chromatography could work, and but it would have the same issues as A and C, but the high performance part means that it will have that greater resolution to tell the difference between things that are so similar.
Mhm.
And I think the reason that I couldn't find like a picture of it is because it's probably some type of complex machine of some sort.
Well, this is the picture they used.
Okay.
Did you get it?
Um, oh, I didn't even realize. I thought you were gonna put it in the.
Oh, email? Yeah, yeah, I just sent it right into the Zoom chat.
Okay. All right, it involves like a horizontal column, like a glass, what? Gas chromatography. Similar to that, separation and quantification, stationary phase, mobile phase, some detector and chromatogram. We can see the difference between the his and the this. Yeah, it seems like it's like well, I mean, it seems similar to like a gas chromatography, but I mean, it shouldn't be. So this should just be just still with like a liquid or water or whatever. But yeah, it seems like the um stationary phase here. Did they say anything about how the state? Did they say like the stationary phase is non-polar or something?
1 second, I have to go on it.
Mhm.
What is eluting strength, by the way?
Eluting strength. Trying to think of the strength part. I mean, like elute is like the first thing that comes out. Um,
It was like on the blueprint exam.
it could maybe mean like that in order to elute, like let's say that this we do this thing and regular histidine elutes first. Um, you can add something that can make it so that this slower eluting thing can elute faster. It's kind of like in a regular kind of column chromatography thing or anion or cation exchange or whatever, where, let's say you want like, let's say it's an anion exchange. So the stationary phase is positive. Mobile phase will be negative. So the negative stuff that you add will attach to the column, and the positive stuff won't and would get eluted first. But then when you want to elute the stuff that's actually stuck to it, you can just pour in a higher concentration of something like sodium chloride, which will have a higher affinity for the stationary phase, causing the thing that's attached to the stationary phase to finally get released and enter and be eluted.
I understand. So let's say like a polar molecule,
Mhm.
a polar, let's say serine.
Mhm.
Serine is going to be like having a high interaction with the stationary polar silica gel.
Mhm.
If I add methanol, methanol has a high eluting strength because, let's say hypothetically, methanol is stronger.
Mhm.
It is going to attach to the silica and knock out serine, and serine's going to flow out.
Yep. 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 Yeah.
Okay. Okay. Great. Wow. That's helpful. Okay. Got it. So I guess the takeaway from this problem is what? Like HPLC is better at splitting like small dipeptides. Gel electrophoresis is more for larger molecules.
Uh, yeah. I think you actually got it uh right by talking about eluting strength because I wasn't really even thinking about that. Um, the eluting strength is going to be awesome for HPLC because like um it's just I don't want to say like it's just like high performance or whatever. My belief is there's some type of pressure pushing it here, right? Something like that. So okay, so like let's see. Um okay, so HPLC can separate really small molecules. That's probably number one. Um and Okay. And
It's fine. I sent you one last problem. I like I'd prefer to go around like 7.
yep.
So
Yeah. So just yeah, just take away. It's highly sensitive. It
mhm,
more precise. It could tell the differences between really small similar molecules.
mhm.
Okay. And you sent it to email?
Email, yes, it should come in. So,
Okay. Got it.
mhm.
Okay. Reaction between an anhydride and phenylethylamine is conducted in organic solvent. Um, which of the following aqueous solutions could be added to separate the amide and carboxylic acids through extraction? Um, okay.
Okay. My question was why
Is it C?
um sorry. Yes, yes, let's see. What is there's like how do I differentiate between B and C? And like yeah, how'd you go about this really?
So we want to separate the amide and carboxylic acid products. And if you add a um a base, like a conjugate base, like the bicarbonate ion, HCO3 minus, it will deprotonate the carboxylic acid, forcing it to be in the aqueous phase. And the amide with that, benzene group is going to be in the organic or nonpolar phase.
Mhm.
And extraction is all about separating things based on how soluble they are in either aqueous or non-aqueous, like organic solvents. So I see A is just sodium chloride. Typically, spectator ions don't do much. I see B is carboxylic acid. We already have one, so that won't help. I see D as methanol, and methanol, you know, is polar. It can maybe uh you know have more of the carboxylic acid in it, since the carboxylic acid is polar. But the best thing to do would be to make the carboxylic acid, instead of just polar, full-fledged charge, and NaHCO3 is gonna break apart into the bicarbonate ion.
How do you know it becomes a base? Just like how? Like I mean,
So this would like whenever you add something with sodium and water, it will dissociate, thus producing this. So just like NaCl will dissociate into Na plus Cl minus.
okay.
So that's how you know that it would break apart into the HCO3 minus. But you should also know about carbonic acid because it's a big, it's like the blood buffer for us, right?
Mm-hmm.
And so that's H2CO3, which is carbonic acid. and it's polyprotic or diprotic, meaning it can lose its first proton to give you HCO3 minus, which is called the bicarbonate ion, or conjugate base. But it can also act as an acid because it can donate its remaining protons. So that can give you H plus CO3 2 minus, and this is just called the carbon. I think it's the carbonate ion. Carbonate.
Mm-hmm.
That. So we want to separate the acid from the amide, and the amide has this big benzene attached to it, which means it's going to be in the organic layer. And then you have the acid, and we can have a decent separation because the acid is polar, but if we deprotonate it, it's going to be like 100% in the aqueous layer.
Sodium bicarbonate is amphoteric, right? Or
Oh yeah,
amphiprotic.
yeah. I think amphoteric, it can behave as a base as well as an acid.
Mm-hmm. So how do you know it's not B, by the way? Again?
Oh, because that's an acid straight up, right? That's just this guy. So if we're trying to separate an acid from an amide, adding, another acid is not going to be useful. Because it's not going to because we already have that, right? So if you just added another acid to this, like if we can't.
Yeah. Yeah. And then you said D, why?
Oh yeah, so that's just methanol,
Right.
and um that, I guess, well, I guess at first they said it was like polar because like ethanol I kind of think of, but it's, let's see. I mean, but it's also organic. I mean, I guess technically you could have organic things that don't have to be non-polar. But yeah, no, methanol would be something like that will assist in um I guess the carboxylic acid being.
It, it doesn't react with either, it says.
Okay. I mean, does it say it doesn't react, or does it say that it's not because it or is not soluble?
It says doesn't react. Polar organic solvent that is miscible with water, but it does not react.
Yeah, yeah.
Yeah,
So
yeah, yeah.
so that would be like a good second option, because you would have most of this in that methanol layer and this in that organic layer. But the best thing to do, let's say you'd probably have 60%, in the methanol layer. But if you use this, you're going to have 100% of this in the aqueous layer.
Mm-hmm. So bases depronate
Yep.
acids, yeah.
Mm-hmm.
Would the Na react with water to form NaOH too?
No, so that's what I was saying about these being spectator ions. They don't really do anything.
How about for C? Na, so it splits into Na and then bicarbonate. But that Na, is it gonna react with water?
You mean this one?
Yes.
No. I mean, like it'll have water salt, like a solvation shell of water around it,
Okay.
but that's it. It's not going to do anything special.
Okay.
Yeah, that goes for like, you know, uh spectator ions. Like there could also be like MgCl2 or you know, that kind of thing.
Hmm.
At most, it can maybe cause something like um well, never mind.
Yeah.
It,
Uh,
ions, yeah.
it's worth to, I mean, like it's worth to memorize all of the ions, polyatomic ones, right? Like sulfuric acids, like sulfate in both ions and the acids, right? Like phosphorus acid, phosphoric.
Yeah, that's another example of a polyprotic one with it's triprotic, yeah.
You know what I want to ask? This will be the last question.
Mhm.
Why for phosphate, it's the the top number changes, or no, like the bottom one changes. You know what I'm talking about? Like for phosphate, it's um
You're thinking of maybe the number of oxygens?
like probably it's just I always for like phosphate, all of that.
Uh-huh.
Trying to find the Anki card there.
Yeah, I think I know what you're trying to
But
say.
like, yeah, but like for sulfate, yeah, so for phosphate and phosphite, right, the oxygen number changes. But for sulfate, the wait, no, the oxygen is still changing.
Yeah, so
Um,
the ITE ending is going to be the one with fewer oxygens,
yeah.
and ATE is going to be the one with more oxygens. And if they're acids, the so I'll like write some of this. So like okay, like fewer, yeah. So oh God, I did this completely opposite way. So the more oxygens, like the salt form would be ending in an ATE, and uh the acidic form would end in IC, and then
Mhm.
fewer it's ITE and OUS. So examples are um PO4 3 minus is phosphate. And then PO3, I think that's the yeah, I forgot the charge for that one, but this
3 minus.
okay,
Yeah.
phosphite, and then H3PO4, phosphoric acid, then H3PO3, phosphorus acid. And this also exists for like SO4 sulfate, SO3 sulfite, NO3 nitrate, and O2 nitrite. And then the one that has even more would be the like for these, it's HCl, so like HCl O2 would be like
Perchlorous.
chlorous acid. Yeah, I'm doing the one in the middle.
Chlor. Okay.
So, and then this one chloric acid. And since we have some extra ones that we're gonna add some more prefixes like hypo to mean less, and then hyper to mean more, but we just for short say per. So then this would be hypochlorous acid. Then this would be hyper or just per chloric acid. So these are for oxy acids, is what they're called. And so yeah, that's like your nitric acid, nitrous acid, phosphoric acid, phosphorus acid, sulfuric acid, sulfurous acid, all of these. So yeah, in general, whichever has the higher amount of oxygens will be ending in the ATE. And if it's an acid, it'll be ic. And then the one with the fewer oxygens would end in ITE, and as an acid would end in OUS.
Okay. Sounds good.
Yeah.
All right.
Yep. So let's have you save this, export this whiteboard.
I just did.
Okay.
Yep, just did.
Awesome. So let's see.
Yeah, I think I like this more because like it also allows me to kind of see what we did after. Because like the videos are, I guess, backloaded, as you were saying, and like you know, I like to sometimes go back.
Yeah, of course, of course.
Yeah.
So yeah, so for today it should be 188.
Okay.
And and also it's good that you're sending me the problems ahead of time. So so we can like go over it like this on like the whiteboard and stuff.
Yeah.
So yeah.
Do you have availability then the same time next week?
Let me see. Do you want to do 4:30 again?
Probably later, just because I want to review I'm taking the exam next Monday, so I
So
have enough time to review it.
5 p.m. Eastern.
Yeah, I mean, do you have an opening later on? Like even later or no? Like what's the latest, hypothetically?
So I try to finish my day at like 8.
Okay, so let's say 5:30.
Okay.
Yeah.
All right, 5:30 Eastern on
Yep.
Tuesday the 30th.
Nope.
All right, awesome. So keep up the good work. Good luck on your practice test.
Yep.
And have a good weekend, okay?
Yep. I'll see you.
Yeah.